All right. If the length of two corresponding sides is similar, or in similar solids are ratios of A to B. So I want you to underline side. If I give you a measurement of one side, am I going to call it meters, meters squared, or meters cubed for one side? Meters. So your units will basically determine the ratio. Looking at A to B. So now let's go to the length. Is my side length meters, meters squared, or meters cubed? Meters. So that means I am not going to change A to B. But on the next one, we're looking at area. How do I denote the area in the units? We say meter squared. So then, just to be consistent with that, our ratio will be A squared to B squared. For volume, we're going to say meters what? Cubed, meaning the ratio will be A cubed and B cubed. The bottom line is the units will control the ratio at all times. So let's actually apply that. On example 1, Mark, let's read.
Two similar hexagonal prisms have edge lengths in a ratio of 2 to 7.
So length, we're going to write length as just meters. What about the apothem? When I give you the side measure of the apothem, what unit do I use? Just meters. So am I going to change 2 to 7? Nope. For the area, we call that meters what? Square. So I need to square the 2 and the 7, which is 4 to what? 49. Okay, let's find C, D, and E with the partner. Go. Talk to your neighbor. All right, Bryce. What is the ratio of the perimeters for part C?
2 to 7.
2 to 7, I agree. Tyler, what about the ratio of the volumes?
8 and 343, right?
8 and 343 is correct. And then Molly, what about the ratio of the lateral areas? 4 to 49. Just let the units control the ratio, all right? Let's actually apply that in terms of the setting up a proportion. Okay, Nolan, let's read example number 2.
Two similar prisms have the edge length in the ratio 2 to 5. The volume of the smaller prism is 40 centimeters cubed. Find the volume of the larger prism.
So we have edge length, and since we're using centimeters, I'm just going to write centimeter right above the length. It is 2 to 5. Because I want to find the volume, I need centimeters cubed. So if I'm starting at 2 to 5 and I cube them, we get what? 8 to 125. That's the proportion we're going to use. So 8 over 125 is equal to 8 is smaller, 125 is greater. They gave us a smaller volume, so 40 is going to go where? Top or the bottom? Top. And then let's cross multiply. Let's go ahead and multiply 125 times 40. It's going to be super clean in the thousands. Did someone say the number? How many?
5,000.
Very nice. So we have 8x is equal to 5,000. Do we need practice dividing the 5,000 by 8?
Yes.
Okay, let's do that together. Here's our 5,000. And there's our 8. 8 can go into 5,000 or 50 how many times? 6 by 48, right? and then bring down one of them. 8 can go into 20 at most how many? 2 by 16. Bless you. And then my last 0. 8 can go into 40? 5. So we have 625 centimeters cubed. Okay, let's try example 3 with the partner. Mm-hmm.
It's no calc, right?
Non-calc, yeah.
So 310.
Thank you for checking.
9 to 1. 36. I did indeed.
It's 5,400, and then divided by 100. Yeah, it's the larger one.
Yeah. Oh, well.
If you're good with the proportion I have on the board, give me a thumbs up. We got 9 over 100 because it was area. Had to square on both sides first. And then when I cross multiply, isn't that 5,400? And 100 pi? Could I just take off 2 zeros? You can formally divide it by 100. Oh, look at that pi. Should that pi be there?
No.
It should be what letter? It should be X. Were y'all like, what is she doing? So we have X equals 54 pi, and what's the unit? Centimeter squared. All right, I'm gonna put a star on number 5. Audrey, let's read number 5, please.
The surface areas of one face of two cubes are 49 centimeters squared and 100 centimeters squared. What is the ratio of the volume of the smaller cube to that of the larger cube?
So right now the ratio given is centimeters squared. And because I want to find the volume, what unit am I trying to get to? Cubed. So we're really looking at 49 to 100. Now going from squared to cubed is not easy. But going backwards to centimeters and then cubing it might be easier. So what is 49, radical 49? 7. And radical 100? 10. Now I can cube them. Didn't we already cube 7 cubed a while ago? 343. What about 10 cubed? 1,000. And it says, what is the ratio? And we found the ratio. Done. That's it. Next page. Okay, Jackson, let's read the instruction on number 6. Now, if it is false, you have to give me a reason as to why. Okay? If it's true, maybe you want to show the work, but you don't have to. So I'm going to give you the first model. If the edge length of a cube doubles, so I'm going to say edge is denoted by meters, and double is 1 to 2. Then the surface area will be meters squared, will be 1 to 4. Has it really doubled? It's been quadrupled. This will be false. So let's do B, C, and D with the partner. Go.
Can I go to the bathroom real quick?
Mm-hmm.
Yeah.
Make it up here. I don't want it in the video.
Edge length meters squared. Volume equals.
And it's 1158.
That is true.
And when you're done, it goes here. Oh,
That is true. Edge length of the cube doubles. That's 1 to 2. And volume. No, that's not true. 2 to 4 to 8. No, that's false. That's 2 to 4. Could be 1 to 2.
Yeah.
1 to 4, 1 to 8.
It's volume.
So it's false, true, true, false.
But for that one? Yeah, for that one.
last one would be false.
Yeah.
Or no, the last one would be true, correct?
when you go
Because that thing's double, and then false volume would be, oh, it's squared,
Yeah.
never mind, you're right. Or cubed.
Cube, yeah.
and then you go to meters squared, so that's 1 to 9, that's 3 squared. But it is.
Why is the last one false?
You're cubing it.
Because instead of 4 times greater on the volume, it should be 8 times greater. So therefore, it's got to be false. All right, let's go straight to the very bottom. My last one, number 8.
Wait, Miss Brockway,
What's up?
can you go back up?
Mm-hmm. We got false, true, true, and false. All right, Nick, let's read number 8.
If the length is doubled and the width is tripled and the height is not changed, how will it affect the volume of the figure?
Okay, let's first label. Here's my length, here's my width, and here's my height. And yes, we need to find the volume of this right here, but let's also write out the changing values. If you want to draw another one, figure not drawn to scale. It says the length is doubled, so it's 18. Are we okay with that? The length has been doubled, right? And then it says the width has been tripled. So if I triple the 6, we get 18. And the height did not change, so I'm going to keep the 7. So let's go ahead and find the volume of the original and find the volume of the second one. So have your partner find one of them and you find the other. Let's not do both. He wants a new one, right, Bryce? New one. Big numbers. Put your head up. Thank you. Okay, Carter, do you have the original volume?
I don't have the original back to go.
You have the new one? Give me a new one.
324.
Ooh.
Oh, is that alright?
Mm-mm. It should be a lot bigger because 18 times 18 times 7, right?
Oh,
2,000?
I don't have 2,258.
68, correct. Inches cubed. Very good. Someone give me the original volume.
378.
378. Let's figure out how many times greater has it gone from original to the new one. So from here to here. It'll be clean. 6. So 6 times greater. Now I'm going to give you a shortcut. Let's say you're like, well, if all I need to find out is how many times greater, here's what you need to do. And this is a good practice for your future ACT and SAT type. So I'm going to bubble this off to the side. I'll be the one using the trick, not the traditional, because it takes too much time. Because our volume formula is length, width, and height, I am going to alter this. It says that length is going to double. When you think of double, what number comes to your mind? 2, okay? When you think of triple, what number comes to your mind? 3. And when you think of the height has not changed, what number is understood? So when I take 2 times 3 times 1, how many is it? Boom.